Good morning, gentlemen. Today is Wednesday, April the 29th, and today we are going to continue our discussion of electromagnetic applications. Today, we're going to talk a little bit about what it means to induce a voltage. There are several practical applications of this, many of which you are probably aware of, although you don't realize that you are aware of them. All right, but today, again, we're going to talk about inducing voltage. So, what exactly is an induced voltage? Well, over the course of the last couple of weeks, we've been talking about the idea that you can generate a current in a wire by running or moving the wire through a magnetic field. You can also induce a magnetic field based on running a current through a coil of wire. And so the moral of the story is that you can induce an electric potential, all right, in other words, a voltage, whenever a conductor moves across a magnetic field. All right, this is essentially the idea behind what's known as the left-hand generator rule. Now, I'm not going to get into the details of that rule here. It's not really important for our discussion, but for those of you who are interested in this kind of thing, just look it up. Spend a little time. Several of you have told me you're interested in electrical engineering. Well, this is the place to start. In any event, the other portion of this is what we call Lenz's law. And this says that the direction of an induced current must be such that its magnetic effects oppose the forces that are inducing the current. All right. And so this is something that we use in creating generators and in transformers, all right, which are the topics of the next two slides. So we'll start with generators, all right? What exactly is a generator? Well, we know that if you move a wire through a magnetic field, the electrons in that conducting wire will begin to migrate. They'll begin to move. And so if you look at the hand generator here, all right, you see somebody's hand actually spinning a handle. And what that's doing is it's causing this coil of wire that you see here to spin. Notice it's shown in its perpendicular view here, as well as its parallel view here. And of course, we're sitting inside the field of a permanent magnet. And so as we turn, the current in this position anyway is coming down this way and going back up this way. But again, notice that there are openings in the brushes and in the coils, so that every time the coil flips, the current changes direction. This creates what we call an alternating current. And that, by the way, gentlemen, is what comes out of the plug in the wall. Batteries or cells, what we call batteries, are actually direct current electricity. The stuff that comes out of the walls is an alternating current, and it's generated by machines that are very similar to the one that you see in the picture. I mean, obviously they're on a much grander scale, and we use things like water and steam and other mechanical sources to provide the kinetic energy to create this current. But in any event, a generator is simply something that uses mechanical energy to convert to create electrical energy. And so the conductor loop is simply spun in a magnetic field. In any power generating plant, there's a big magnet and a coil of wire, all right, and one spins around the other, okay? Now, the other thing is, once we've generated this electricity, we want to send it to people's houses, okay? But unless you put a generating plant, every 20 feet or so, you're not going to be able to conduct that current over those long distances. So you'll notice that there are two kinds of electrical wires. The ones that run along the poles outside your house, But if you're ever driving down the highway, you sometimes, like the thruway, you see these massive towers with these huge wires that are running from one place to another. Well, those big wires have to be fed from a little wire. And then the power has to be taken from the big wires and dropped down to get into your house. And in order to do that, we use something called a transformer. And this is one of the simplest things. It's actually absolutely amazing. All a transformer is a block of iron or maybe some other ferromagnetic material, something that can be induced to be magnetic, although it's not necessarily magnetic initially. And so what happens is you run a current right through here and it comes out the other end. I may have drawn that in the opposite direction. I can't actually tell. But the current comes in, runs around this coil on one side of this iron ring. And what that does is it generates a magnetic flux. And the magnetic flux in this case is shown going clockwise around the ring. But notice that on the other side of the ring, there's a second coil of wire, not wrapped quite as tightly this time. And so in the secondary winding, all right, you're producing, the magnetic field is producing a current, and the current is coming out this way. Now, so current goes in, that current creates a magnetic field. That magnetic field then creates a current in a second set of wires. Notice there is no direct transfer of electrons in a transformer. All right, current comes in, goes around one coil and goes back out. And then the current is generated in the other coil. All right, and so what the function here is to change the potential difference or the voltage of an alternating current. Now, how does this work? Well, there's a couple of mathematical rules, and they're very straightforward. They're directly proportional. The number of coils of wire in the primary coil divided by the number of coils in the secondary coil equals the voltage in the primary coil divided by the voltage in the secondary coil. All right, very, very straightforward relationship here. Now, if the number of coils in the secondary coil is greater than the number of coils in the primary coil, we call it a step-up transformer. All right, because what that'll do is it'll create a voltage in the secondary wire that's greater than in the primary. On the other hand, if the number of coils in the secondary coil is less than the number of coils in the primary coil, then we call it a step-down transformer because we are decreasing the voltage. Now, have a look at the picture on the right-hand side of the screen. What kind excuse me, what kind of transformer is this? All right, very good.
It's 6 o'clock.
Oh, thank you, Jesus. For those of you who guessed that this is a step-down transformer, you are absolutely correct. Okay, now, the other relationship that you have to realize is that the amount of power remains constant. And so the formula for power is V times I, or current voltage times current. And so we can use that for a variety of things as well. All right. Last but not least, the percent efficiency of a transformer is the ratio of the power, the secondary over the primary, times 100. And most transformers will give you somewhere between 90 and 100% efficiency. Never 100%, but damn close. All right, damn close. Okay, so that brings us to example number 2. Maybe. There we go. So in example number 2, and where is example 2? Come on. There we go. An ideal transformer that has 200 turns in its primary coil. So NP equals 200 turns. And 50 turns in its secondary coil is connected to a 120 volt AC power line. Okay, so 120. And the secondary current is 3 amps. We want to know Vs, IP, and PP. I said PP. And PS. Now, remember the PP and PS are going to be the same, all right? So it doesn't really matter which one we actually calculate. So let's have a look at this, all right? If we go back, remember, here's the formula. NP over NS equals VP over VS. So, you know what? I'm not even going to do that. I'm just going to erase this. Come on, baby boy. There we go. All right. So 200 over 50 is going to equal 120 over Vs. All right. We're looking for the secondary voltage here. All right. Do a little bit of quick arithmetic. 50 times 120 is 6,000, and divide that by 200, and that's going to give me a Vs, a voltage of 30. All right, so the secondary voltage is going to be 30 volts. All right, so obviously this is a step down transformer. Now, how do we calculate the value of IP? All right, well, in this case, all right, go back to our equations. We know that the, come on, that the voltage times the current equals the voltage times the current. And so, so VP IP equals VS IS. All right, I'm just going to get rid of that for a minute. So VP is 120. IP is what we want. And that's going to equal to VS, which we just calculated as 30, times IS, which we know is 3. So 3 times 30 is 90, divided by 120. And so that's going to give me an IP value of 3/4, or 0.75 amps. Okay. Now, in terms of the power, we now know the secondary voltage, the primary voltage, the secondary current, so it doesn't really matter, but P equals, remember, V times I. So we can do this either as 120 times 0.75, which is 90, or we can do this as 3 times 30, which is also 90. So power, either primary or secondary, is going to be 90 watts. Okay, so there we are. All right. Now, one last little piece of information that you can take home and stick under your pillow or send to the tooth fairy or something, is that it is possible to induce a current in the secondary coil by taking a direct current and flipping it on and off. You know, on, off, on, off, on, off. You can then induce a current in the secondary coil. And there are ways to do that that we're not going to get into today. But in any event, the transformer is typically for an alternating current scenario. Okay, and that, my friends, is the end of our discussion for today. Happy Wednesday. I am going to attach or I'm going to ask you to make sure you look at that combined circuit problem before tomorrow. I'll post the answers tomorrow afternoon, and hopefully you'll be ready for the quiz on combined circuits on Friday.